All right, today we're going to build on what we know about bonding by introducing a topic called electronegativity. Now, before we get too far, we should probably define what electronegativity is. So, as we watch this, make sure you write down on your notes. You should have got a packet already, and write down these notes as we go through them. So, electronegativity. First off, electronegativity is how much an atom wants or attracts an electron from another atom. So, what exactly does that mean? Well, it's almost how, I guess you could say, how greedy an atom is about an electron. So, how much it pulls on that electron towards itself in a bond. It does a lot for us. One thing it does is it provides a model for how atoms bond and how different atoms bond. It helps us predict what could happen if we know what's going on with electronegativity. Now, as you can see down here, all these atoms of electrons have values. It goes from 0, which is almost no electronegativity, to 4, which is the most, fluorine. So here's a question. Why do you think the noble gases right here have nothing? Not a 0, not a 4, but just a dash right there. And the reason is because noble gases don't need electrons. Remember, they have their valence completely filled, whether it be helium. Remember, helium, if we draw helium, there's the nucleus. It has 2 electrons in its first energy level, which is means that it has a full, not an octet, but a full shell. Of course, the neon and the rest of them would have 8. But remember, helium only has 2 to start with. Okay, so what else do we know? The electronegativity increases across periods and decreases down a family. So really what that means is metals as a whole have lower values. So we kind of look at the metals here. Remember, most of the metals are right here. They have lower values. Most of them are under 2. So with a few close to 1.9, but for the most part, very, very small. Okay. On the flip side, we know that nonmetals have higher values. And we can kind of see here that the higher values, for the most part, are going to be nonmetals. So again, the nonmetals are in the red, whereas the metals are in the yellow. So that's important. Strong nonmetals, the strongest ones we know of would be our friends, the nitrogen right up here, oxygen, fluorine, and chlorine. These are the ones that really are very, very strong. They like to hog all of the electrons. Weak nonmetals include about the rest. As you can see, those anything above 3 is considered pretty large here, so that's kind of the cutoff point right there. And as you can see, the arrow kind of shows as a whole, they increase as you go up and to the right. Let's look at some types of bonds. What do we do with electronegativity? Well, for the most part, electronegativity can help us figure out. Now, we talked about covalent bonds, we talked about ionic bonds. We haven't really talked about metallic bonds quite yet, but we will very soon. So let's kind of get into 2 types of covalent bonds. There's nonpolar and there's polar. So an example of nonpolar would be Cl and Cl, 2 chlorine atoms bonded together with a covalent bond, sharing. That's when electrons share equally, non-polar. Nobody's pulling. Polar meaning one side has an advantage and one side has an imbalance. This is a perfect balance. It's like if you were sharing something with your sibling and you guys shared it perfectly, all right? You were very, very careful about how you shared it. A present maybe you got, maybe you got some sort of gaming system or an article of clothing, and you set up a very strict schedule. All right, you can wear the shirt on Mondays and Tuesdays. I'll wear it on Wednesdays and Thursdays, and we'll take turns on the weekend, something like that. That'd be a perfectly shared way of doing it. Now, the key here is the difference of the En, the electronegativity, is less than 0.5. So you go back to the periodic table that I just showed you on the previous slide, and you subtract one value from the other value and find out what that is. So if you look at chlorine, put your finger on chlorine, it's 3.0. 3.0 minus 3.0 is 0. So obviously it's nonpolar. Oftentimes a strong nonmetal and a strong nonmetal together will be nonpolar, or a weak nonmetal and a weak nonmetal together. Both nonmetals, so that's what's key. Next up, we have polar. Well, that means there's an unequal sharing of electrons. They're sharing them, but they're unequal. So for example, it'd be like if somebody, two brothers, got some sort of gaming system and they were supposed to share it as a present. But instead, one brother kept it in his room and never let the other brother play. Now, technically, they are sharing it, but it's not a very good sharing, right? So as we look here, electrons shared unequally. So as you can see, this brother over here is taking it a lot more. So in this case, chlorine is taking it a lot more. So if I looked at this here, if it's greater than 0.5 and less than 1.7, typically it's going to be a polar covalent bond. So if I look at hydrogen, hydrogen has a electronegative value of 2.1, whereas chlorine has a 3.0. So that's what the delta means. The delta means the difference. So 3.0 minus 2.1 is 0.9, and 0.9 is found perfectly in between these two. So that means it's definitely polar covalent. Now we talked a lot about ionic bond, and an ionic bond is when we have a metal and a non-metal. So you know that that is going to be a transfer. Up here, when we were talking up here with covalent, covalent are sharing. Ionic are not sharing, so you might want to remind yourself of that. It's an attraction between something that's charged positively and something that's positive negatively, a cation and an anion. This is when you got a big difference, so it's greater than 1.7, very large. A metallic bond, and again, I'm just kind of going through this quickly. The ionic bond we already talked about. Metallic bond we haven't talked about before, but that's just when you have some metals, two metals. Cesium, Cs, is a nonmetal. We know that because it's on the left side of the periodic table. And basically, it's a sea of electrons. They kind of just share those electrons very, very loosely. All right? They share those electrons, and all the electrons it's kind of like a utopia, right? And anytime you see a metal and a metal, that means it's a metallic bond. Again, a metal and a nonmetal, ionic bond. And up here, typically you're thinking non-metal, non-metal, always. So that's kind of your key here. If you notice non-metal, 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 that's going to tell you it's always going to be a covalent. Again, metal, non-metal, ionic, metal, metal, metallic. So if we look here, the directions say we're going to classify each of the following bonds as nonpolar, covalent bond, polar covalent bond, ionic bond, or metallic. Now there's a few things that we can kind of focus on that really help. Number one, anytime we see covalent bonds, those are between two non-metals. Okay, so anytime we see non-metals, so for example, right here, this is a non-metal and a non-metal. Hydrogen, even though it's on the left side of the periodic table, it's a non-metal, right? Also, same thing here, sulfur and oxygen. Those are both nonmetals, all right? And then last but not least, well, actually, I take that back. There's two more, chlorine and nitrogen, nonmetal, phosphorus, fluorine, nonmetal. Okay, so right away we know those are going to be some sort of covalent bond. The question would be then, is it going to be a nonpolar or a polar? That's where we pull in those values. So we would kind of look and say, okay, well, if we know that let me change this here. If we know that carbon is 2.5, and hydrogen, and I'm getting this from the periodic table, is 2.1. I have a pretty small number that says 0.4. So keep that in mind. Also, let's kind of look at some of the other things here. We got iron and zinc. These are both metals. So metal, metal, that gives us a hint right there. So let's just kind of go down the line. We got some hints here. Now the positives and negatives, speaking of hints, kind of tell us that there's charged particles, and that reveals something. So just some background there. So if we have a metal and a metal, we know that metals and metals are always going to be a metallic bond, okay? Metal, metal is always a metallic bond. And we know because on the periodic table, they're both metals. This one here, with calcium and bromine, a positive and a negative, a metal. So this is a metal and a non-metal. Again, I'm looking at the periodic table, and that is ionic. Anytime we have a metal and a non-metal, that's going to be that. So let's just put that up there as a little note for this. If I have a metal and a non-metal combination, I know that's going on right there. Super. Now, again, these two covalents are always going to be a non-metal pairing. We already said that, of course, metallic bond is going to be metal, metal, two metals, okay? So the question then is this nonpolar or polar? Now we said this is nonpolar because the difference between this is so tiny. 2.5 minus 2.4. 2.5 minus 2.1 is 0.4. It's a very tiny number, so it'd be nonpolar. Now, we can tell this right away is true because if you notice, there's no signs above it. Right here, that's called sigma. That number sigma, that means slightly positive and slightly negative. So since this is slightly positive and slightly negative, we know that that's a polar one. Okay, now we can also tell because sulfur has a 2.5 and oxygen has a 3.5. That's a huge difference right there. 3.5, 2.5. Remember, I'm getting that from the periodic table on the first page of this. So that's a difference of 1.0, which tells us that's definitely polar. Same thing here, same idea as before if we have a positive and a negative, but more importantly, we have a metal and a non-metal. So right away that tells us it's ionic, just like over here. Nitrogen and chlorine are both non-metal, so we know it's either type of covalent bond, but it's a very small difference. So that means that it's non-polar. Nobody's pulling at these. Last but not least, again, two non-metals, but there is a slightly positive and a slightly negative, and the difference is very large. Polar covalent. In fact, the difference is phosphorus is 2.1. Pretty much anytime fluorine's involved, you're pretty good chance you're going to have a huge difference between these, and that's going to be 1.9, and it's going to tell us it's a polar. So keep an eye out. If you see fluorine, that's a pretty good chance you're going to have a polar covalent bond. All right. Okay, so good deal. And that helps there. Let's take a look at this right here, and we're going to get to this soon, but I want to show you some things. There's a lot going on here, but something called a cation, an anion, a positive and a negative. How would we do this? Well, it's really easy when they're the same charge. Magnesium's 2 plus, oxygen's 2 negative, so we need a 1-to-1 ratio, Mg to O. This is what it looks like right here. Exchange of electrons. 2 electrons, this one and this one, go right there. 8 and 8, we're happy. But what happens when you have an issue? What happens when you have 2 plus and a 1 negative? How do we fix this? Well, what we want to do is have 2 Cls. If we have 2 Cls, 2 negatives would equal 2 positives. So this is sort of what it looks like right here. So you can pause and draw that. It's pretty complicated, but what we see here is 1 Ca and 2 Cls. Everybody is happy. Make it just a little more complicated, and you'll see that aluminum has a 3 plus and sulfur has a 2 minus. How can we do this? Well, what we're going to do is just take the 2 and put it over here, and put the 3 and put it over here. What do I mean by that? We would do Al2S3. So again, I'm just taking the 3 and switching it over here, and the 2 and switching it over here. So I have 2 and 3. And this is what it would look like, which is crazy, right? But it does give us a combination that makes the octet happy and makes the charge very, very easy to see that it's going to attract each other, okay? Hopefully that helps. Hopefully that is something that you can see and understand. If we don't take the notes, we'll talk about it tomorrow. We'll get through it, and hopefully it'll make a lot more sense.